Chapter 8 doesn't really introduce any new big ideas. It's just going to be applications of some things we've already learned. So we're going to start off the chapter by talking about equilibrium, revisiting equilibrium. We've already talked about it once, but we're going to talk about it again now that we have torques in our toolbox. And then we're going to talk about spring forces and elasticity, how things stretch a little bit. So that's kind of a new topic, but it's also just an expansion of our force discussion. So first off, let's revisit equilibrium. In a previous segment, we've learned that if the sum of the forces on an object are zero, then that object is in equilibrium. But we have to be a little bit careful. This is really only an approximation that works if we're in the particle model, right? So this is only true in the particle model. Now that we're moving beyond the particle model and we're talking about torques, it's no longer enough, right? So let's say that I've got this package of mac and cheese here, and I could apply equal forces to either side. Is it in equilibrium? Yes, it is. And even if I push real hard, it's still in equilibrium because the force this way equals the force this way. The force of gravity this way equals the normal force this way. Everything balances. So equal force this way, equal force this way. Got to be in equilibrium, right? What about this? Not in equilibrium. Still equal forces, not equilibrium. Here's a series of slides that illustrates the same point. If we're in the particle model, then two opposing forces create equilibrium if those forces are equal and opposite. So this particle is in static equilibrium. It's not moving, it's not accelerating. Those forces balance out. Net force is zero. Now, we could move to beyond the particle model, and as long as these forces are in line with each other, we're still in equilibrium. But as soon as I displace these forces from each other, in other words, if they're not acting at the same point, then we are no longer in equilibrium. So in the particle model, we have net force is zero. That's enough. But now that we've moved beyond the particle model, we need to have both the net force and the net torque equal to zero. So we'll add this condition here. We need the sum of the forces to equal zero and the sum of the torques, or the net torque, to also equal zero. In this scenario here, we see the box has net torque and net force is zero, so this box is equilibrium. But here we have net force is zero, but the net torque is not zero, and so this is a box that is not in equilibrium. So for an extended object, we need to have no net force in the y, no net force in the x, and no net torque. That is what we need in order to have an equilibrium situation. The nice thing is that now that we have torques in our toolbox, we can solve a variety of equilibrium problems that we could not solve before. Okay, so there's a whole class of problems that are equilibrium problems. Once we've identified this as an equilibrium problem, then we're going to approach it from a sum of the forces and sum of the torques equals zero. So that's why, I started off this segment by saying we're not really learning any new big ideas here. It's just how to apply some ideas we've already learned. So what are our steps here? Well, we need to draw a picture. And so we're going to draw forces. And again, much like in the last chapter, we've moved beyond the particle model. So we want to actually draw an extended picture of the object. It should be simple, right? We don't want to be spending a bunch of time creating a great work of art. So just a simple, quick drawing. But it can't just be a dot anymore. And we need to draw those forces where they actually act. And I'm going to encourage you to practice using our convention, where our forces are drawn with the tail at the location where the force is applied, pointing away from the object. It's not the only way to do it, but it is the standard conventional way to do it. And we do it that way because it makes for nice, clean drawings that are easy to interpret. Then we should draw our coordinates and identify a pivot point. Recall that with forces, we always needed to have an x and a y direction. We had to decide what's our best coordinate system. Well, here we might be using forces and torques, so we need to define our x and y coordinate system and also decide, are we going to call clockwise or counterclockwise positive? And so we kind of have these interacting coordinate systems. We need x, y for forces, we need counterclockwise, clockwise for torques. And of course, our standard convention is we call counterclockwise positive. And now we apply Newton's second law. Since these are equilibrium situations, the sum of the forces in the x is zero, in the y is zero, and the sum of the torques is zero. Now I will say that often we often have problems that you can solve with just the sum of the torques equation. And so I suggest that you start there, right? I've listed this as sum of the forces in the x, then sum of the forces in the y, and then the sum of the torques. But we're going to have a whole bunch of problems that we can solve by just looking at the sum of the torques. And so I suggest you start there, and then only go back and look at the sum of the forces if the sum of the torques is not enough. In a way, the sum of the torques is just a more powerful tool. We get a little more leverage, if you will, with the sum of the torques. And so let's start there. Often, it will be the only thing you need. Then we solve, as we always do, right? And we assess. Again, we're in this mode of problem solving where we don't just go hunt for the equation we're going to plug into, right? We're in this mode of problem solving where we use these instructions, we use Newton's second law to create the equation that we plug into and solve in step 4. And then in step 5, we assess, does our answer make sense? Did we end up with a positive value if we were expecting a positive value, a negative if we were expecting a negative, things like that, as we've been doing all semester. One tricky aspect of solving these problems is this right here, identifying a pivot point. That step right there can be a little bit tricky because in equilibrium problems, we're usually talking about situations where things are not rotating, right? In chapter 7, it was often pretty clear where our pivot should be because we had things rotating about some point, and it's like, oh, well, that point it's rotating about, that's clearly our pivot. But in these equilibrium problems, we're often talking about things that aren't rotating. And so picking the pivot point can be a challenging step. The good news is there are no wrong answers. There are maybe more convenient choices and less convenient choices. But as long as you go through the process of picking a pivot, then it all works. So here I have my hammer, as shown in the PowerPoint also. And the first thing we should just say is my hammer in equilibrium? Yes, it is, right? It is. It's not accelerating. And that means it doesn't have any translational acceleration. And it also has no rotational or angular acceleration, right? So this is absolutely in equilibrium. That means the net force is 0. That means that whatever weight the hammer has is balanced out by the normal forces produced by my fingers. We're getting pretty good at those now, right? But also, since it's in equilibrium, the net torque is 0. We can only evaluate net torque about some point, right? So we should maybe be more specific. The net torque is 0 about what point? About any point. It's not pivoting. It's not rotating. So it doesn't matter, right? I could call where this finger is right here. It certainly could pivot about that point, right? It's not. So I could call the pivot point right here. I could call the pivot point right here, where this finger is. Heck, I could call the center of gravity the pivot point too. It doesn't really matter exactly what's the more convenient choice or less convenient choice. Well, only practice can tell you that. But we just need to go through the process of picking a pivot point in order to evaluate our torques. In many of the problems, it will be fairly obvious. Well, it'll say, it's attached to a pin, free to rotate at some point. And that's a good clue of what the problem is suggesting to use as your pivot. But it's important to recognize that if the object isn't rotating, it doesn't matter. The torque is 0. The net torque is 0 about any point. So we just want to try and pick the point that's the most convenient. Okay, let's dive in and do some examples. Here is a quick clicker question type example. And I guess maybe you might try and kind of reason your way through this, just kind of in your head, and then also try applying the steps. So it's real tempting, I think, on a straightforward problem like this to just kind of think through it. You can kind of just reason your way through. And maybe you can reason your way through and get to the right answer, and that can be satisfying, and that's not a bad thing to do. But we also want to be sure that we are applying the techniques we're learning, our problem-solving steps, to a straightforward problem like this, so that we're getting practice using our problem-solving steps, so that when we get to a more involved problem, then we're ready for it, and we know how to use those steps, and we can do it on a problem that we maybe just can't kind of fudge our way through. Okay, so why don't you give this a shot? Again, try it first with just kind of reasoning through it. What do you think it should be? And then try it with the steps and see if the math agrees with your just sort of, man, what do you think it should be? Okay, I'll see you on the other side. Okay, I'm going to solve this using our steps, and we'll see if that doesn't make sense. What does the scale at the center of the massless rod read? So I'm just going to draw a quick sketch of my massless rod. You know, it's got this pin over there on the left-hand side, right? And so, you know, I think that's going to be our pivot point probably, right? We've got a force of the scale here. And then we have 1,000 newtons pointing down right there. In this case, we're actually not going to end up using forces. In these problems, man, I'm not going to give you problems where it's an equilibrium problem and we really need to tilt our coordinate system. Remember, we tilted our coordinate system in order to put the acceleration in one dimension. We have no acceleration in these equilibrium problems, so a standard coordinate system is going to work for you. And similarly, there's no reason not to just call counterclockwise positive. That is our standard. And we've identified our pivot. It's right here where that pin is. Now, I've suggested that we apply the net torque first. The net torque equals 0. So sum of the torques equals 0. We're going to start there. And if that's not quite enough information, that's okay. We're not going to panic. We might go back and use the sum of the forces equals 0 also. But we're only going to do that if we find that this is not enough to get the answer. Okay, let's remember our definition of torque, right? Our definition of torque is Rf sine phi. Okay, so what torques do we have? We have a torque here, and we have a torque here. Now, certainly there are forces acting at this pin, aren't there? In fact, what direction would that be in? Well, let's see. We've got a scale here and something pulling down here. So I think actually there's some force right here pushing down. And in a more challenging problem, I might even ask you for that. In this case, though, I'm not going to. I'm just asking for the force of the scale, right? What does the scale read? And notice that this force on the pin at the pivot, well, it's acting at the pivot, so it creates no torque, right? So we don't need to worry about this force right here in our sum of the torques equation. To be specific, R is 0 for this force applied at the pivot. Okay, so moving on, we've got the force of the scale. Is that positive or negative? Is that creating a positive torque or a negative torque? Well, and we see that the force of the scale is trying to rotate it counterclockwise, and so that is a positive torque. And so we have a positive torque. Where is it applied? Well, if we call the length of our bar L, then the force of the scale is applied in the middle at L over 2. You might be saying, it didn't tell us how long the rod is. How on earth can we answer this question? Well, let's have faith that it is not a trick question and call the length L and just move on, see what we get. Okay, so we put that there because that's where the weight is acting. Excuse me, that's where that force of the scale is acting. It's acting in the middle, L over 2. And then we're calling it force scale. Sine of 90 is 1, right? This is 90 degrees. And so sine of 90 is 1. I'm not even going to write it. Then we have the 1,000 newtons. That's trying to rotate this thing clockwise. And so that should be negative all the way out at the end. L times 1,000 newtons equals 0. Again, sine of 90 is 1. There's our equation. Notice that my L's cancel. So if you freaked out and were like, hey, I can't solve this. I don't know the length of my bar. You freaked out too early. Okay, here we go. And now we just see, do some quick algebra. F scale equals 2,000. Okay. Does that make sense? Well, it does actually. It does actually. The 1,000 newtons out here at the end, in order for this force to create the same torque as this, it's got twice the lever arm. This one must have to have twice the force, right? Twice the force with half the lever arm gives the same torque, right? You know what? We could sum our forces now, and we could actually figure out what this force in the pivot is, right? Here we have 1,000 newtons down, This is 2,000 newtons up. Well, gosh, this right here must be 1,000 newtons down. And so you can see that it does all jive here. Okay. And PowerPoint does agree. Woohoo! A couple of tricky things here, right? Notice that we did not call this torque right here negative because the 1,000 newtons was pointing down. We called this torque negative because the 1,000 newtons is trying to rotate this bar in a clockwise sense. We didn't call this one positive because F sub scale is up. We called it positive because F scale is trying to rotate the bar in a counterclockwise sense. Let's do another example. So here's a classic equilibrium problem. You've got this beam, it can rotate over here, and it's going to ask us to find the tension in the cable. A uniform beam of length 1 meter and mass 10 kilograms is attached to a wall with a cable. The beam is free to pivot at the point where it touches the wall. Okay, so it's really giving us a strong suggestion that we should make that our pivot point, isn't it? What is the tension in the cable? Okay, so let's draw our quick beam here. I'm going to call that L. It does give us that that's 1 meter. The beam does have some mass, doesn't it? And so what forces are acting on here? Well, certainly we've got the weight, right? So a lot of times I see students draw the weight acting out here on the end. Ooh, no. A uniform beam has its weight acting in the center. Okay, so there's the weight. We have the tension over here. There we go. Now, we've got the pivot here, right? Now, a lot of times I'll see students just solve this with these forces using some of the forces. And it doesn't work. Why not? The reason is because there's some force in the pivot over here, right? There's some F pivot. And what direction is it in? Well, certainly it's got to have a component upward or this end would just fall out, right? We can imagine that. But also notice tension is pulling in this direction, but the beam's not accelerating. So there must be a component of that force in this direction. So there is some force like this, right? And we don't know what angle it's at. We don't know what magnitude it is. We could call it F pivot. So we can give it a name, but we don't know anything about it. And so notice here, we've got one unknown here, this tension. We've got another unknown, this pivot. And we also don't know what angle it's at. So essentially, there are 3 unknowns. You cannot solve for 3 unknowns with 2 equations, right? So you can't just get away with using forces and get this problem right. If you use forces to solve this, you probably ignore this force in the pivot. So I see students try and solve these problems a lot by using just forces, and it seems like you've got enough information, but you're ignoring this force right here. If we include this force, which you have to, it's part of the whole thing that makes this beam do what it's doing, then you don't have enough information with just the sum of the forces. You have to use the sum of the torques. Okay, having said that, this force in the pivot, it creates no torque because it's acting at the pivot, right? Its radius is 0. And so we see here, this is some of the power of this technique of using torques to analyze something that's not moving. It's kind of surprising, right? It's kind of surprising. It's not rotating, yet we can use the sum of the torques. And we see why it's such a powerful tool. Because all we have to do is put the pivot point at some unknown force, and that force never shows up in our math. Okay, so we've got our setup, we've picked our pivot point, we're going to use our standard counterclockwise as positive. We've drawn our forces at the location of where they're acting. We've been careful, we've drawn them with the tips at the location where they're acting, pointing away from our object of interest. In this case, our object of interest is the beam. Next, we should apply the sum of the torques. Equals 0. Let's remember that our definition of torque is Rf sine of phi. So, the sum of the torques. I see one torque, the weight. The weight, well, there's 2 torques here, but let's start with this torque right here, caused by the weight. Notice it is trying to rotate it in a clockwise sense. That is negative. It is acting at the middle because it is a uniform beam, and we should draw the weight acting at the center of gravity. So that's negative L over 2 times W. The angle is 90 degrees. Sine of 90 is 1. Then we have a positive tension. tension is positive because it's trying to rotate the bar in a counterclockwise sense. Now, what is the angle between R and F? Remember, what is phi? It's the angle between R and F. Let's just draw R. R is right here. And so, indeed, the angle given is the angle we need. And so we should write sine of 40 equals 0. Notice again my L's cancel. That's nice. And so we can do some solving, and we end up with T equals W, which is mg, over 2 sine of 40. And when I run my calculator, I got 76 newtons. It's a good number, makes sense. The weight would be what, 98 newtons? So this is a little less than the weight. It makes sense. Some of it's being carried over here. Okay, it seems reasonable. Okay.